La 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 la. Bouncing? Okay, cool. Oh. I will begin with a word of prayer. So. Dear Father, we thank you for this day again, Lord. I thank you for these students. Pray with us today. Help us to understand a little bit about the theory in chapter 12. And just again, Lord, help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so let me just kind of give you a recap of where we are. So first I'll turn in your homework, hand it over, get that over with. I should have the solution to your last homework posted today. I have that done. I'm still working on the solution to this one. I hopefully will have it done soon. Sorry for the delay. So, if you have been reading chapter 12, right, you should realize that I have not followed chapter 12, right? And generically speaking, I will continue to not follow chapter 12, not quite precisely. Now, I followed it pretty tightly for the... okay, it's fine. I followed it pretty carefully from sections 12.1 to 12.5, right? Well, on the convergence of series. We followed it pretty closely. I more or less showed you the proofs in the book. Fine, whatever. And I spent longer trying to describe convergence and divergence of series than I have in some past semesters. I hope that you guys understood some of that material. If you're still lost on that material, sections 12.1 through 12.5, do not despair. You have a lot of good company. My advisor, who taught calculus for decades and decades, said that when he taught calculus 2, and he is really good teacher, much better than me. He said if he was teaching calculus 2 and he had more than 20% of the class really understand convergence and divergence of series, it was a good semester. So, if you're lost, you have a lot of good company. We don't want to stay lost, of course, so we'll try to fix it. But just realize it's difficult. I mean, I'm not going to try to sugarcoat it for you. That convergence, divergence stuff is hard. So what I was trying to do past that point is just describe to you formally, and when I say formally, I just mean without regard to convergence, the theory of power series, how to calculate it, how it relates to a function. How can we reproduce a function with a power series, right? And so I set aside questions about domains of power series. I mean, I introduced the concept of the domain of a power series, which, by the way, is section 12.8. I started with section 12.8, right? So now I'm paying my dues. I'm going to go back to section 12.6. I'm going to talk about theorems in 12.6, all right? And then we'll go on. So here's the first thing, Taylor's theorem. Theorem 12.6.1. If you have f is n plus 1 times continuously differentiable on an interval I that contains 0, and if x is an I, then you can write f of x as well, we recognize this. I called this what? The nth Taylor polynomial at 0. You could say Maclaurin polynomial, I guess, if you wanted to. F of 0, f prime of 0, x plus dot 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 plus the nth derivative at 0 over n factorial, x to the n, plus Rn of x. And more than that, Taylor's theorem. Sometimes this is said to be Taylor's theorem with the integral form of the remainder. Well, the remainder can be written as 1 over n factorial, the integral from 0 to x, of the n plus 1th derivative of f at t times x minus t to the n dt. This is Taylor's theorem. All right. Now, how do you prove that? The proof in gory detail, with all the careful steps, is in your textbook on page, where is it? 604. But if you think back, I've already actually made you think about this, whether you realized it or not, back, way back, section 8.2. way back. In the integration by parts section, number 78, there's a problem where you derive this formula in the n equals 2 case. You have to integrate by parts, I think twice, and this formula pops out. So if you look back at number 78 in the homework, which you guys asked me about because it's weird. It's a weird problem, right? That's the n equals 2 case of this. And in fact, the proof of Taylor's theorem in this format is exactly the same as the proof of the homework problem. You just integrate by parts a bunch of times on this integral, and out pops that formula. Just that. So that's Taylor's theorem. That actually is not, we don't find ourselves using this theorem too much directly like this. What we really use is an amalgam of this and what's down here. So the next thing is Lagrange's formula for the remainder. Lagrange's formula for the remainder states that, in fact, this remainder term, you can recast, instead of being this pesky integral, you can actually find some particular value c that's either between 0 and x like this, if x is positive, or it's between x and 0 like this if x is negative. And so for some c between 0 and x, all right, you can plug that into the n plus 1th derivative, and that divided by n plus 1 factorial times x to the n plus 1 encapsulates the remainder term. That's actually kind of surprising, that the whole remainder can be lumped into this one thing like that. It's cool. That's surprising to me, really. But there it is. And I showed you the proof of that last class. That was the thing I put up on the projector that we worked really with big M. That's what we proved. That was in my old school calculus notes, which I will at some point finally give you a link to, and I'll put in course content if I haven't already. I forget. As you may have noticed, I've been sick and not thinking entirely clearly. Some days worse than other. But anyway, before the dust settles, I will send you a link to that and so forth. Actually, the proof doesn't matter to us too much. Once we know, the proof is essentially a generalization of the mean value theorem proof. Once you know it, then you can use it. All right, and then the next step then is if the n plus 1th derivative, I'll take your question in a second. If the n plus 1th derivative is bounded by m on the interval I, then we actually get a bound on the remainder term like this, right? And you just did homework where you use this, I hopefully successfully, right, to bound the error in the Taylor polynomial over its application to some certain interval, right? That's what this is for. At least that's one application of it, right? Like you saw in the homework from 12.6 that you just turned in. What was your question, Travis?
I was just wondering if your school notes are on
Mm-hmm. They are, but I will try to post that for you guys. It's actually in my Calc 1 notes even, because I proved Taylor's theorem in Calc 1, left to my devices, because logically that's where it goes. Well, there's many illogical things we do in the calculus sequence. I would say one of those is requiring you guys to study convergence and divergence at this point in your education. I mean, I personally think that material we just went over is easily 10 times harder than anything else we do in this course. But it's the custom to cover it, so here we are covering it. Everybody else is doing it, must make it right, right? I mean, it is part of the standard curriculum. We might argue with hundreds of years of tradition. Okay. So let me get to the big picture. That's just some due diligence I have to do in here, right? Now let me get to the main point of today. There are really oh no, here it starts. There are really two types of convergence to think about in here. So I'm about to make a really subtle point to you guys. The one thing you might think about is this. If the nth remainder, as we're just talking about over there, goes to 0 as n goes to infinity for each x in some interval I, then f of x is equal to f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 times x squared plus dot, 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 dot. Let me put that into words. In other words, if the remainder goes to 0, What that means is that the Taylor series at 0, or if you like the Maclaurin series at 0, which is generated by the function. Generated by the function in the sense that, how do you generate it? You take the derivative and you plug in 0. You take the second derivative, you plug in 0. You take the third derivative, you plug in 0. You create this series according to Taylor's theorem, right? So if this Rn of x goes to 0, then f of x is in fact, or rather I should say, the Maclaurin series actually converges to f of x. I'm talking about the convergence of a series to a function. That's not a kind of convergence that we've actually defined in here, nor will I, except to say that. So if that's the case, if the function actually matches the Taylor series that it generates, then the function is said to be analytic at that point. So an analytic function is one for which the power series of the function, in fact, is an honest-to-goodness reproduction of the function at that point. Or you could also talk about it some interval. For example, let's look at a positive example before I show you the weird example. The exponential function is a good one. We can show that the exponential is analytic on the reals. This is example 3 in section 12.6. So what's the deal? E to the x is equal to 1 plus x plus 1 half x squared plus 1 over n factorial x to the n plus this remainder term plus this Rn of x, right? To show that the exponential is analytic, I need to show that this remainder term goes to 0. You guys with me? So how do we show the remainder term goes to 0? This is the question, right? We use Lagrange's formula for the remainder. Lagrange's formula for the remainder says that Rn of x is equal to e to the c over n plus 1 factorial times x to the n plus 1 for some c that's between 0 and x. Now either it's 0 and x or it's x and 0, depending on if x is positive or if x is negative. Right? But either way, Lagrange's formula for the remainder says there's some c in this interval with endpoints of 0 and x for which the remainder is just equal to that. All right? But then what you can do is you can bound. You can bound the exponential. You can bound the derivative, the fn plus 1, which is also just e to the x, right? And you can look at the maximum of that on this interval. It's either going to be e to the x if x is positive, or it's going to be e to the 0 if x is negative. Anyway, it's a number for a fixed x. We should think of x as being fixed in this argument, like basically below here. X is a fixed number, okay? So, so what do we have? We have the remainder is bounded by this m, all right, which has possibly some x dependence, but x is a fixed number here. The absolute value of x to the n plus 1 divided by n plus 1 factorial. What happens as n goes to infinity? X is fixed here. X doesn't have an n dependence. Well, that's an easy one, right? If that's on the quiz, you ought to be, I mean, if I was asking you a sequence question, what happens to this sequence as n goes to infinity? Everybody would be like, there's a factorial in the denominator, right? I mean, if I had to show that it goes to 0, it might be kind of a pain, but you know, this x, however big it is, if x is like 10, once you get past about n equals to 10 or 11, then the bottom is growing way faster than the top, right? Because the top just keeps being like 10 times 10 times 10 times 10, whereas the bottom starts being like 10 times 11 times 12 times 13 times 14, and it just gets worse from there, whatever x is, right? You know the story. The factorial wins, right? So this sequence goes to 0 as n goes to infinity. That shows that e to the x is analytic from 0 to x, but guess what? X is arbitrary, so this shows that, in fact, the exponential function is analytic on the whole real line. So that's what I've been glossing over. When I claimed for you that after we did those calculations over there and we showed that the Taylor series for e to the x was what it was, I mean, we calculated this Taylor series for e to the x the other day, right? 1 plus x plus 1 half x squared, and we did examples with it, right? But this is what's actually required to prove that I can honest to goodness write that equality there. That e to the x really is really, that this series really converges to e to the x. I must show the remainder goes to 0. That's what's technically required. You're like, well, is it even possible to have a function where you can generate the Taylor series, right? And yet the function isn't matched by its Taylor series? Like, is that even possible? Well, Lagrange would have told you no. I mean, I think anyway. Like, Lagrange wrote a calculus book in, I forget what it was, like 1788 or something. I don't remember the release date. I wasn't there. I guess he didn't announce it by Twitter or whatever. But anyway, at the start of Lagrange's book on calculus, he starts by describing a function. And his description of a function is, in fact, that it is analytic. He starts by, he says something along the lines of, suppose f of x is analytic. He says, suppose f of x is a function. And then he says, in other words, f of x is equal to like a naught plus a1 times x plus a2 times x squared plus a3 times x cubed plus dot, 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 dot for appropriate constants. They actually took that as a primary definition of what a function was for a time because it's so general what things are analytic. But that's in fact not, that's limiting. That removes part of the world, the mathematical world in which we live. There's this other example, this one. Here's the deal. It's 0 for x less than or equal to 0. And then it's e to the minus 1 over x squared for x positive. So I graphed this thing in red. So it's just 0 all the way up to 0, and then it smoothly goes up, and it approaches 1 asymptotically like that. This is known as the bump function, by the way, or it's an example. It's not exactly the bump function, but it's, let's say it's related to the bump function. The bump function actually goes back down again, the one I'm thinking of. It smoothly goes up to 1 and then goes back down to 1, like that. But that doesn't matter. Here's the thing. You can calculate, well, what's f of 0? By definition, 0. What's f prime of 0? Well, if you calculate the derivative from the left, it's obviously 0, right? You have a constant function. It's first, second, third, fourth, nth derivatives are all 0 from the left. Those are, I don't need any kind of fancy schmancy analysis to tell you that. If it's constant from the left, all of the derivatives are 0 over here, right? From the right, though, there's some slippery analysis that's got to go on. From the right, I have f prime of x is like equal to this, which is minus 2 e to the minus whatever x squared over x cubed. That's indeterminate type. You got to like L'Hopital that thing. After you work out the details, though, you'll see it goes to 0. And in fact, all of the right first derivative, the right second derivative, the right third derivative, the right fourth derivative, you can prove. It goes on and on. In fact, all of the derivatives, the right derivatives of this function are 0. I don't want to spend the time to actually prove that for you. Just trust me, it's true, okay? If you'd like, I can make it a homework problem. I think I might have actually made this a homework problem. I think it's number 63. Did you already do it? Did you already try to do it? Was this due yet, or is this in the second part of 12.6? It might have been a later 12.6 problem, so it's not due yet. Yeah, it's probably due Friday. Oh yeah, use a graphing utility to draw the graph of the function, blah, blah, blah. Oh, oopsie, I did part A for you. Sorry. And I'm describing how to do part B. All right, getting back to the point. So the point is, all of the derivatives and the function is 0 at 0. So what's the Taylor series generated by this bump function at 0? It's the 0 function. This green line is the Taylor series. As you can see, if you look at any neighborhood around 0, this function is not replicated by its Taylor series. you could not show that the remainder goes to 0 for this example. In fact, it doesn't. This smooth function, it's smooth. You can take infinitely many derivatives of it. It's smooth, but it is not analytic. Its Taylor series does not match it close to the origin. This is the cautionary tale. This is why we have to show Rn of x goes to 0, because there are examples like this out there. Don't ask me for another one. It's the only one I know. It's actually not entirely true. There are other ways of like taking this and twisting it a little bit, like take this and multiply by sine, or look at like, I don't know, there's various ways of basically doing the same thing, but So that's point number one. That kind of convergence, the question of whether the function's analytic or not, is a delicate, difficult question, I think, personally. And I don't really want to test you guys on that. I really don't. Because even something as simple as this exponential is still kind of like a lot to think about, right? The other examples, which aren't too bad, and you can really fight your way through them, sine and cosine, those aren't bad. I've done those in other semesters. They're not too bad. And if you read 12.6, he basically shows you all of your standard examples are analytic over the appropriate domains, right? So if you don't mind, I'm going to allow you to gloss over that question, and I am also going to gloss over that question. So I'm going to turn the focus of our attention now to part 2 here, which is given a power series, all right, what's its domain? So notice that now I'm just starting with the power series, like I'm starting with section 12.8 basically. I'm just saying, here's a power series, what's its domain? I'm not trying to compare the power series to a given function for which I can beg the question of analyticity. What was the question? So let me show you an example of this sloth. Now, that said, I will, I taketh away, but I also giveth. And what I will giveth you is multiplication and division of series. Those are computations that you ought to be proficient at, and the book ought to have taught you. I don't think he has multiplication and division of series in chapter 12, but that's, unless maybe I'm missing it. I could be missing it. I've read it a couple times, but I haven't focused on that question yet. And looking in the index seems like cheating. So I will make sure I teach you how to multiply and divide series. I think that's an important computational technique, especially as engineers, that you'd like to know. That's one of the things we need for applied calculations. It's certainly something that I should leave you with from this course. All right, so that's what I will make up for glossing over the remainder going to 0 with multiplication and division of series, just so you feel like I'm not cheating you. All right, so this, for example, is a series. And yeah, it's alternating. What I'm saying is, in fact, sine of x is equal to s of x. All right? That's the kind of glossing I'm talking about. To prove that, what would I have to show? I would have to prove that the remainder term goes to 0 by studying Lagrange's form of the remainder. It would actually be even easier than what we did, because the nth derivative is bounded by 1. Essentially the same formula, the same argument shows you that the remainder goes to 0. But I'm trying not to talk about that. So let's study the series s of x equals to minus 1 to the k over 2k plus 1 factorial, x to the 2k plus 1. I want to talk about what's the domain for this series. All right? How do we figure that out? Well, I'm just doing some name calling to start with. I'm going to call that a sub k. That's the kth term, right? Okay? And so for fixed x, that's just a number, right? And this is just a series, so I can use the ratio test, right? So what I do is I don't look at the series itself. I look at the absolute value of the series, because that's easier. I don't want to think about that minus 1, right? And besides, I need to use the absolute value if I'm going to apply the ratio test, right? Because I got to apply the ratio test to what? Positive terms, right? So if I apply the ratio test without putting the absolute value there, I'm in trouble. So let's do it. All right. So there's a k plus 1. Now, do you guys understand why I did 2 times k plus 1 here? It's because the formula is, so I'm replacing k with k plus 1. Do you see that? Because these terms are, that's that. Does that make sense? Somebody in an earlier section was lost here. Then we divide by a sub k, the absolute value of it. So that's absolute value of x to the 2k plus 1, 2k plus 1 factorial upstairs. Right? And we do a simplification very much like the ratio test we've already worked in here. I bring the power outside the absolute value and both places, and I just multiply. This is 2k plus 2 plus 1, which is 2k plus 3, right? Remember up here, 2k plus 3 factorial can be simplified as 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. So that means I can cancel basically what? This piece, oops, sorry. I can cancel the 2k plus 1 factorial with most of the 2k plus 3 factorial, but I'm still left with two things, right? I'm left with these two pesky factors here and that residual absolute value of x squared. What happens as k goes to infinity? X is just a number, right? It has no k dependence. It just sits there, and the division by 2k plus 3 times 2k plus 2 clearly makes this go to 0. Yay, ratio test applies, right? We get what? Convergence. In fact, we get absolute convergence of the original series because I've just showed that the absolute value series converges, right? For what x? What was the x dependence of this argument? There was none, right? It goes to 0 independent of x. So it follows then that the domain of this power series is in fact the whole real line. A little bit of language for you. This is called the interval of convergence. Or, as we will soon grow fond of abbreviating it, the IOC. You can also call it interval of convergence if you'd not like to call it IOC, but I will use the abbreviation IOC because I get sick of writing interval of convergence. Likewise, the radius of convergence is the ROC, which I will either call ROC or I might just call it R, if that's okay with you guys, because I get sick of writing radius of convergence. Now, that's an example. So what I'm doing here is showing you a couple of examples. We're going to see a general pattern, and then we're going to state a theorem about what are the possible domains for power series. Yeah.
Does that mean that the domain is always symmetrical on your sides if there's a radius?
Right. That's what we're getting to. We haven't, I mean, it's just an example at the moment, but our next example is this series, the sum xk equals 0 to infinity of x to the k. All right? So that's a series. It's given. It's a power series. Right? I can't even ask the question of analyticity in this case because I don't have some other function, right? Okay, let me stop talking about analytic. That's the harder thing. I said I'm not going to talk about it too much, so I'm going to shut up. All right. So here's a ratio. Let's call this thing a sub k again, just to give it a name. So the absolute value of ak plus 1 divided by absolute value of ak is just straight up the absolute value of x to the k plus 1 divided by the absolute value of x to the k. I hope we can all simplify this, right? So it's absolute value of x. What do we need less than 1? This is what's required, right? This is a condition which is required for ratio test to work. If the absolute value of x is less than 1, then the ratio test says, hey, series converges. In fact, of course, what we have is that the absolute value of the series, term by term, converge. In other words, we have absolute convergence of the series on the open interval -1 to 1. And consequently, we have that the series converges on the open interval from -1 to 1. Now, at this point, all I can safely conclude, now, the earlier section didn't ask me about this, but they didn't know what this meant. This is called a subset. Do you know what it means for A to be a subset of B? So if here's B, here's A is a subset. A subset of B means that if X is an element of A, that implies that X is an element of B. Subset. So the interval of convergence has to include -1 to 1, not included, both of them not included. Logically, that has to be a subset of the interval of convergence. And I also get from the ratio test what? Notice that if the absolute value of X is greater than 1, then what does the ratio test say? Yeah, but I guess that's not directly useful because X could be negative, right? And then I would get that the absolute value series converges. That wouldn't diverges. I guess that wouldn't immediately say that the original series diverged, would it? I don't know if I have that theorem, but if X is greater than 1, ratio test fails, and at a minimum, and we can go back, we can see that if you look at the X to the K, it's not going to 0, right? Therefore, S of X is not an element of the reals by kth term test, right? So we could at least use that argument, even if the ratio test isn't directly helpful to us, right? I mean, if the absolute value series diverges, that doesn't necessarily mean that the series diverges, right? Yeah, there's the conditional convergence to worry about. So just to be clear, if the absolute value of X is greater than 1, then X to the K does not go to 0 as K goes to infinity, right? Consequently, this series diverges by the kth term test for any X which has magnitude larger than 1. We agree? So we have that something inside -1 to 1 is in the interval of convergence, and that leaves us then 4 possibilities, right? -1 to 1, -1 and 1 not included, or you could have the Clopin set, or the opposed set, or the closed set. I mean, these are stupid terms. Some people will call this this is a Clopin set. This is an opposed set. Just stupid terminology. It's like half open, half closed. Either the right or the left endpoint included. But those are your 4 choices, right? Now, to decide which one of those 4 it is, you have to check the endpoints. And that's what I do over here, right? The endpoints are pretty easy to check. If we plug in X equals to 1, we get this. If we plug in X equals to -1, we get that, right? These both clearly diverge by the kth term test, right? And so from that, I learn that, in fact, this guy is indeed the interval of convergence. All right? Let me show you another example. Oh, yeah, the radius of convergence here is what? Huh. Sorry, I'm just thinking about things. Yeah, the radius is 1. I actually, once I know this, I can tell you that the radius of convergence is 1. let's see here. Let me look at something like 1 over 1 plus x squared. And I want to do something a little bit different. Let me put a 3 here. All right, so I'm going to change that to, let's see here, this is 1 over three times what? Right? So this leads us to study what series? Yeah, geometric, I heard. So you look at this and you can see A is equal to 1/3 and R is equal to minus x squared over 3. And so with that identification, this should be the same as the series. K equals 0 to infinity, 1/3 minus x squared over 3, all right, to the k. Let me clean this up a little bit. This is the sum. K equals 0 to infinity of 1 over 3 to the k plus 1. And then upstairs I've got a minus 1 to the k, and then x to the 2k. Now I showed you the man behind the curtain here, all right? But imagine yourself in the land of Oz, and they just give you this, all right? Let's just study this as if it's an innocent example disconnected from its origins, right? So forget its origin story. I told you the origin story, ignore it. Just consider this as a series. Let's find its interval of convergence. How would you do it? I'll call that a sub k just as a point of discussion. We look at the absolute value of a sub k plus 1 divided by a sub k. We're trying to, very boring here. This is the kind of boringness that you had sought for in the last series of lectures, this single-minded devotion to one test, as if there's no other tests to think about, right? That day has finally come. The ratio test, yes. Well, yeah, I'm not, the thing is, it's not me making it easy. It's that it is a theorem that you can decide the open interval of convergence for power series by the ratio test. And if I state it a little bit different, in fact, it will also tell you the radius of convergence inside a slightly modified ratio test. I'm not sure that results in the book or not. I will try to state it for you anyway once I get a chance and regroup and so forth. Anyway, so what do we got? We've got x to the what? 2 times k plus 1, right? Divided by what? 3 to the 2k plus 1. I'm sorry, not 2k. 3 to the what? 3 to the k plus 2. We're supposed to take the absolute value of that times what? Let's see here. We've got ourselves a 3 to the k plus 1 divided by x to the 2k. Where did the minus 1 to the k go? It's like the absolute value ate it. Let's see here. So we have x to the 2k plus 2. Let me just get to the point here. We got what? X squared divided by what? 3? Do you guys agree with 3? Yeah. Okay. Math, after all, we should remember, it's not based on absolute truth. It's based on a consensus. So since you guys have agreed on this consensus, I guess we're okay. Huh. Yeah, I guess I don't really believe in that, do I? Let's see here. I guess it's just as well. Let's see here. I'm sorry, I digress. So this is the ratio, right, of the absolute value of subsequent terms. If we want the ratio test to be helpful, we need this to be what? This less than 1 then implies what? That the sum of the absolute value of AK converges, and hence, the series A sub k converges, right? So what is this condition then, yeah? We have the absolute value of x squared less than 3, right? What's that? What's that imply? Indeed. Yeah, less than square root of 3. That is true, yes. So therefore, the radius of convergence is equal to the square root of 3, and the IOC includes minus root 3 to root 3. Again, whether or not plus or minus root 3 are actually in the interval of convergence or not, that is a question we must address separately. Sorry to bring all those other convergence divergence tests back into play, but there they are. Hey, but for infinitely many points, we got convergence. That's not too shabby. One test, infinitely many points. Pretty good economy of argument. Now, if we look at x equals to the square root of 3, what do we get? Or let's start out with a minus 1. Minus square root of 3, what do you got? You just got to plug it back in and look at it directly, okay? In lieu of other arguments. Oh. So, hey, this looks kind of good. I think this is what? Square root of 3 squared is what? Right, I could rewrite, let me point out, this can be rewritten as minus 1 to the 2k times square root of 3 to the 2k, right? Minus 1 to the 2k is just 1. So the minus gets eaten by the even power. And that just is what? 3 to the what? So we have 3 to the k over uh-oh, bad news. Not a bad example, just bad news. I mean, for this series, it's very bad news. It's, well, if this series set out as a young series, it left its mother and father and went out to be a real number, then it's a sad, sad series. It's a prodigal series. It should return home to the world of non-real series and live there, because it's not real, right? Diverges, right? By kth term.
So we shouldn't include that in our interval.
No, that is not in the interval of convergence. Definitely not. And likewise, square root of 3 is not an element of the IOC. Through a similar argument. Why is this totally unsurprising? The reason this is totally unsurprising is that if you go back and look at how do you get from there to there, it requires that the ratio, right, which is to be less than 1, right? And when you get ratio is equal to 1, that's a divergent geometric series. So I kind of already knew that the endpoints were going to get thrown out because I know how geometric series diverge. But if you forget that it's geometric, right, if you forget its origin story, then you'd have to check these points separately if it just came to you as a series that you didn't know walking along the street, you know. So anyway, long story short, interval of convergence is in fact equal to minus square root of 3 to square root of 3. And there you go. So to figure out the domain of a power series, it's a kind of like a 3-step test. Step number 1, ratio test. You apply it, it will tell you the open interval of convergence as well as the ratio of convergence. Step number 2, check the left endpoint if you got one. Step number 3, check the right endpoint if you got one. Right? Now steps 2 and 3 are not even needed if you have some precious and wonderful example, like our first one, where the ratio is 0, the ratio test comes out to 0 independent of x. In that case, you get the radius of convergence is infinity, and the interval of convergence is the whole real line. So, yes, sir?
So that means that it diverges at negative square root 3 square root 3, but what happens in between there?
It converges by the ratio test.
Any number.
Yeah, that's what this shows. If x is between plus or minus root 3, then the ratio is less than 1. Consequently, this converges by the ratio test, which means that the original series converges. This is not an accident. This always has to happen. That's what we're going to go over tomorrow, is the proof of that the domain of a power series always has to either be the whole real line or a finite interval. Or there's one other case. It could just be the center point. There are stupid series like that. So anyway, more on that tomorrow. Thanks, guys. Oh, your quiz. I'm going to go write your quiz and send it to you. You can turn it into me tomorrow, if that's okay. If you'd rather do it in class tomorrow, we could do that, but no? Okay, yeah, I thought maybe.